Separable equations. A separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of y times a function of x times a function of y. So, for example, notice that we have this dy dx is equal to e to the 2x divided by 4y cubed. I can think of this, that e to the 2x over 4y cubed, I can think of that as e to the 2x times 1 over 4y cubed. So here, this is some function of x, and this is some, I'll call it h of y, some function of y. So I have the dy dx factored as a function of x times a function of y. Now, it's called a separable equation because I can sort of separate everything that involves the dependent variable on one side and everything that involves the independent variable on the other side. So what I will do here is multiply, basically, by the 4y cubed. And so I can write this equation as 4y cubed dy is equal to e to the 2x dx. And now basically, to solve the equation, I integrate both sides. So, the integral of 4y cubed dy, that would be y to the 4th. The integral of e to the 2x dx would be 1/2 e to the 2x. Now, we should have a plus c1 on the left and a plus c2 on the right. Generally, what we do is we just put a plus c on the one side. But now, we usually want to solve for the y variable if possible. And in this case, we can solve for the y variable. And so we could write that a solution of this is y is equal to the 4th root of 1/2 e to the 2x plus the constant. And notice that that constant is under the root. Solve dy dt is equal to t e to the t over y times the square root of 1 plus y squared. I think this would be a good one for you to try on your own. So now would be a good time to pause. I see that this is a separable equation, so let me rewrite it as y square root of 1 plus y squared dy is equal to t e to the t dt. I'll integrate both sides. Alright, so now I have to figure out how to integrate this. It's a good thing we've learned all those techniques. So let's see, integrating y times the square root of 1 plus y squared dy, I think this will work with a u sub. I'll let u equal 1 plus y squared, then du would be 2y dy, so I would need a 2 here and a 1/2 on the outside. And so then that would become 1/2 integral u, 1/2 integral root u du. Okay, and so this ends up being 1/2 times the square root of 1 plus y squared. I shouldn't have written it like that. The antiderivative of u to the 1/2 is u to the 3/2 over 3/2. So I'd have a 1 plus y squared to the 3/2 over 3/2. Now on the right hand side, I'm integrating t e to the t dt. Okay, that looks like when we needed to use parts. So I'll let u equal t and dv equal e to the t. So then du is equal to is equal to 1 dt, and v is equal to e to the t. So then that would become uv, so that's t e to the t minus v du, the integral of e to the t dt. And so then this becomes t e to the t, and the antiderivative of e to the t, so that's minus e to the t plus a constant. All right, so simplifying a little bit, the 1/2 and this 3 multiplied by, that's the same as multiplying by 2/3. So this is 1/3 of 1 plus y squared to the 3/2 equals t e to the t minus e to the t plus a constant. Multiply through by 3. 1 plus y squared to the 3/2 is equal to 3t e to the t minus 3e to the t plus a constant. All right, 3 times a constant is still a constant. All right, now I'd like to at least isolate the y square. So I'll raise both sides to the 2/3 power. So 1 plus y squared would equal the quantity 3t e to the t minus 3e to the t plus c to the 2/3 power, and then I'll subtract the 1. So y squared is 3t e to the t minus 3e to the t plus c, all raised to the 2/3 minus 1. And I'll stop there. That's good enough for a solution. And it at least has the y variable, the dependent variable, isolated, even though it's not to the first power. Solve. dv ds is equal to s plus 1 over sv plus s. Again, this would be a good time to try this one out on your own. So now would be a good time to pause. The first thing I would notice here is I can write dv ds as s plus 1, and I can use some factoring here and write that as s times v plus 1. And so that's s plus 1 over s times 1 over v plus 1. So what I'll do is I'll multiply by the v plus 1 and I'll multiply by the ds, writing this as v plus 1 dv is equal to s plus 1 over s ds. And then I'll integrate both sides. Now the left-hand side is relatively easy. All right, antiderivative of v plus 1, that's 1/2 v squared plus v. On the right-hand side, s plus 1 over s, well, that's the same as s over s is 1 plus 1 over s ds, isn't it? And so then that would be equal to s plus natural log absolute s plus a constant. And this would be very difficult to solve for v because it is quadratic and it does have that linear term. So we won't solve this. We won't try to isolate the v. We'll just leave it as is. Here's another one for you to try. Solve. Y prime is equal to 8x to the 7th times y over the natural log of y. So the first thing I would do is rewrite y prime as dy dx. So I've got dy dx is 8x to the 7th y over natural log y. Get everything with the y together, get everything with the x together. So multiplying and dividing correctly, I can write this as natural log y over y dy is equal to 8x to the 7th dx. Integrating both sides. Let's see, natural log y over y dy. I think I'll need to make a substitution there. If I let u equal natural log y, then du is 1 over y dy. And I've got that 1 over y dy, don't I? And so then I have the integral of u du, and so that would be u squared over 2. So this ends up being 1/2 natural log y squared. The right-hand side is simple. That's just x to the 8th plus a constant. and I'll leave it there. Find a solution of the differential equation that satisfies the given initial condition. So even though it's not a, so here we have y of 0 is negative 4. I'm sorry, y of 1 is negative 4. So even though it's not y of 0, we still call it an initial condition. All right, so here we have dy dx is 1 plus x over xy. So notice that that's 1 plus x over x times 1 over y. All right, so separating the variables, I would have y dy is equal to 1 plus x over x dx. Integrating both sides, and the antiderivative of y is what? 1/2 y squared. Right-hand side, that same trick we used before, 1 plus x over x, that's 1 over x plus 1. So that would give me a natural log absolute x plus 1. Now I can leave off the absolutes because we're told that x is greater than 0. So I'll just write natural log x plus x plus a constant. Now, we're told that y of 0 equals 4. I'm sorry, y of 1 is negative 4. So that means when x equals 1, y equals negative 4. So I would now have 1/2 of So I would now have 1/2 of negative 4 square is equal to natural log of 1 plus 1 plus c, and I can solve for c. Negative 4 squared is 16, half of 16 is 8, the natural log of 1 is 0, plus 1 plus c, and c is 7. So, the solution of the differential equation that satisfies the initial condition, right, the solution of this problem, of this initial value problem, is 1/2 y squared is natural log x plus 7. All right, here's one for you to try on your own. Now would be a good time to pause. All right, so let's find the solution of this initial value problem. dy dx is 7x to the 6th y, and y of 0 is 8. I'll separate the variables. So I would have 1 over y dy is equal to 7x to the 6th dx. Integrating both sides, the integral of 1 over y dy is the natural log absolute y. Right-hand side, the integral of 7x to the 6th is x to the 7th plus a constant. Now, in this case, I can easily solve for y by exponentiating. And so, and we'll not worry about the absolute here. I can write y is equal to e to the x to the 7th plus c. And remember, that means y equals e to the x to the 7th times e to the c. And e to the c is a constant. It's a constant multiplier. And so what we would usually write here is y equals some constant times e to the x to the 7th. Now, we're told that y of 0 is 8. So that implies that 8 is equal to c times e to the 0 to the 7th power. All right, so 0 to the 7th is 0. E to the 0 is 1. So 8 is equal to c times 1, which implies that c equals 8. So therefore, my solution to the initial value problem is y equals 8e to the x to the 7th power. Now that we've seen techniques on how to solve separable differential equations, let's look at an application. So one application that often leads to separable equations is these sort of mixture problems. So here's the type of problem we might see. A tank contains 50 gallons of solution at a concentration of 2 pounds per gallon. Pure water is pumped in at a rate of 4 gallons per minute. The mixture is well stirred and drained at the same rate. Find the amount of salt in pounds in the tank at any time measured in minutes. All right, so the question is, how much salt is in the tank at any time? All right, so that's our unknown. Find the amount of salt in pounds. So that's the unknown. That's a function of time. We're actually trying to find a function that satisfies this problem. Okay, so I'm going to let A of t represent the amount of salt, and that's going to be in pounds, at t minutes. And let's make a note. Let's note that we have an initial value. The tank initially contains 50 gallons of solution at a concentration of 2 pounds per gallon. 50 gallons at 2 pounds per gallon. So A of 0, the amount of salt initially in the tank, is 100 pounds. Now, for these type of mixture problems, a general way to approach this is to consider the rate of change of the amount of salt. dA dt. The change in the amount of salt is going to be the rate in minus the rate out. So when you're trying to solve these types of problems, the general method is to sort of think of this idea and then work from there. Now, dA dt, that's a change in the amount of salt with respect to time. That's got to be in pounds per minute. Let's keep that in mind. All right, so dA dt must be a rate in. What's coming into the tank? Pure water is pumped in at a rate of 4 gallons per minute. Pure water at a rate of 4 gallons per minute. So, something's coming in at 4 gallons per minute, and it's pure water. So how much salt is in it? How much salt is in that water? Well, it would have 0 pounds per gallon. Now, the mixture is well stirred and drained at the same rate. So it's leaving the tank at 4 gallons per minute. But now at any time, how much salt is in the tank? Well, at any time, there are A pounds of salt, and there are 50 gallons in the tank, right? The solution's coming in and leaving in at the same rate. So at any time, there's 50 gallons of solution in the tank. Okay, so it's leaving at a rate of 4 gallons per minute by A pounds per gallon. Notice that if we look at these individuals, right, gallons per minute and pounds per gallon, notice what happens to the units. The gallons reduce out, and I'm left with pounds per minute. The gallons reduce out, and I'm left with pounds per minute. So the units match up. And I've got dA dt is equal to, now this whole first term goes away. But in the second term, simplifying, I'll have what? Negative 2 over 25A. All right, so there's the differential equation, and now I can solve it. It's a separable equation, so I can write this as 1 over A dA is equal to negative 2/25 dt, and I'll integrate both sides. So then natural log absolute A is equal to negative 2/25 t. And we're assuming that the amount of salt is positive, so we don't really need an absolute value in this context. Exponentiating, oh, I should have a constant here, shouldn't I? Plus a constant. All right, now, exponentiating and using that same little trick that we saw in the previous exercise, I can write that A is equal to some constant times e to the negative 2/25 t. Now let's consider this solution for a moment. Does it make sense? Pure water is pumped in, stirred, and is leaving at the same rate. What should happen to the amount of salt over time? Since pure water is coming in, we're not getting any salt added to the solution. The amount of salt has to be decreasing. And what we remember about exponential functions, base e, is that if that k value is negative, we get a decreasing function. So that's reasonable. We note that a of 0 is 100. And so then, since what we remember about exponential functions, this c, that's the initial value. Right? So that's, in this case, a of 0. So my solution is a is equal to 100 e to the negative 2/25 t. This is the equation that describes, that models this situation. All right, here's a similar problem. It's not exactly the same, but I think this would be a good one for you to try on your own before you look at my solution. All right, let's read through the problem. A tank initially holds 10 gallons of fresh water. At t equals 0, a brine solution containing 0.5 pounds of salt per gallon is poured into the tank at a rate of 2 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. Find the amount of salt in pounds in the tank at any time measured in minutes. All right, so I'm going to start with the same basic idea. I'm going to call A of t the amount of salt, and that will again be in pounds at time t in minutes. And I note that the tank initially holds 10 gallons of fresh water. Initially holds 10 gallons of fresh water. So that means that the amount of salt at time 0 is 0. All right, let's write the differential equation. dA dt, the change in the amount of salt with respect to time, and remember that that's got to be, that rate has to be pounds per gallon. Pounds per minute, excuse me. dAdt, the units have to work out to pounds per minute. Okay, rate in minus out. All right, how's it coming in? A brine solution containing 0.5 pounds of salt per gallon is poured into the tank at a rate of 2 gallons per minute. All right, so it's coming in at 2 gallons per minute, and it contains a ½ pound of salt per gallon. A ½ pound of salt per gallon. How's it going out? It's leaving the tank at the same rate. So again, 2 gallons per minute. But now, how much salt is in it? Well, there would be A pounds of salt in the 10-gallon tank. Simplifying, dAdt, 2 times 0.5 is 1, so I'd have 1 minus 1/5 A. So there's the differential equation. It is separable. So I can write this as 1 over 1 minus 1/5 A dA is equal to dt. Using a substitution, right, if I let, well, now I have to integrate both sides. And here I'll use the substitution, u equals 1 minus 1/5 A, so then du is equal to negative 1/5 dA. So I would need a negative 1/5, that would mean I'd need a negative 5 on the outside. Otherwise, it then becomes just the integral of 1 over u du. So this then becomes negative 5 natural log absolute 1 minus 1/5 A. The right-hand side is just t plus a constant. All right, exponentiating, we'd have 1 minus 1/5 A. Oh, I need to divide by the negative 5 first, sorry. Dividing by the negative 5, natural log absolute 1 minus 1/5 A is equal to negative t over 5 plus a constant. Now, can we take care of that constant now? We know that a of 0 is 0. That means when t is 0, a is 0. So let's see, that would give me then that the natural log of 1 minus 0 is equal to 0 plus a constant. The natural log, so that's the natural log of 1, which is 0, which implies that the constant is 0. All right, so I don't need that constant anymore. Exponentiating. 1 minus 1/5 the A, 1 minus 1/5 A is equal to e to the negative t over 5. Subtract the 1, negative 1/5 A is equal to e to the negative t over 5 minus 1. Multiply through by negative 5. And A is equal to negative 5 e to the negative t over 5 plus 5. And so there, this function represents the amount of salt in pounds at any time t. T is measured in minutes. All right, that concludes the presentation for this section.